And what we're looking at is two popular methods for controlling speed. One of them is using something called a tach generator. And the other one is using something referred to as an encoder. And we have both of them up here. So this is the actual motor right here. And then we're using this DC motor as a generator. Now what determines the amount of voltage we get out of this thing? So this is a permanent magnet motor, so we can't control the strength. So what determines the amount of voltage you get out of it? So when we swing a conductor through a magnetic field, it induces voltage conductor. What determines the amount of voltage we get into the conductor is the strength of the magnetic field, which we're not changing, right? It's a permanent magnet motor. The number of conductor loops, so this guy has a wound rotor, and when it's spinning through those things, we're not changing the number of loops. And the third thing is the speed of motion. So what we're doing is when we speed up the motor, it speeds up the tach generator. The tach generator outputs voltage that is proportional to speed. So if we knew, so you can see here's my meter right here, and I'll change the speed of the motor. When I slow the motor down, what happens to the output voltage of the tach generator? Yeah, it decreases. And all we're doing on DC motor, of course, is change the voltage on the armature. So I'm going to be able to see that. So right now we're getting 4.75 volts in the motor. Here's the setup right here. So this is the motor, this is the tach generator. And of course, when I decrease the speed of the motor, voltage drops. So if I knew what voltage 2.86 volts represented, what speed that was, then I could vary easily, because it's linear, right? You understand? So it means this guy varies exactly proportional to the speed. But then I have to know what that is. So you have to actually measure the speed of the motor to get that indication. These are very, very popular. PLCs, both our Siemens PLCs have A to D converters. So what happens is it brings in a voltage and then it converts that over to a binary number for us. And now that binary number, that makes sense. So these are called tach generators, and they're very popular. And what we would do is so what we would do here is like a pod. I could use a pod, and I could come up here and set it to 100, but that 100 generates that voltage. This goes into what we call an error amplifier. And if the set voltage and the feedback from the tach generator don't match, it'll adjust the speed of the motor to run at the set speed. Okay, y'all understand that? Another thing that's very popular is devices that we refer to as encoders. So an encoder is nothing but a wheel that has a bunch of holes. That's all it is. And then we have something that we refer to as an optical interrupter. This is a through the beam. This is a through the beam sensor. Okay. It's called an optical interrupter because what we want to sense breaks the transmitter. Here's the emitter, here's the detector. This emits line, so here's the detects line. You put something in there that breaks it, we know it's present. But what we do is we take our encoder on these things, and then of course the encoder just fits down to here. So when it spins, it actually breaks. And of course, the resolution of the encoder depends on the number of holes through it. So this guy here's got 8. Now why we do that? Because our speeds are given in revolutions per minute. So I could come up here and I could count the speed over a minute. Now my tach gauge is only update every minute. That's not good. A lot of things can happen in a minute. So the more notches we put, the less time we have to take it, right? You understand that? So what this means is we can take this, we can get a better resolution, so we can count it over a lot shorter time. So maybe I might count it over a second, right? Makes sense. This way. And then of course I count it over a second. If I can count it over a second, then I can update my RPM every second. But you got to understand, this guy is looking at revolutions per second, and then our pulses, but our RPM is minutes, right? Yes. So we got to do a little math. But PLCs, well, so PLCs, just about all PLCs have what they call high-speed counter now. So it means I could bring the output of this thing into a high-speed counter. That sucker has no problem with the speed of the motor. So we could put 32, 40 notches on our encoder, like get a real high resolution. Now we can count it over a shorter amount of time. That's all. They could have notches. They could be, some encoders are what we call variable reluctance, where they have just metal tabs sticking up. And then what they have is they have draw this. Let me bring up PowerPoint. This is what they use on your card for your automatic brake system. They use variable reluctance pickups. They're very, very rugged. They're very reliable, and that's the big thing. An automobile looking for something that's very rugged, right? So, but it works on exactly the same principle as the optical encoders do. Except what it does is the tabs on the encoder. So usually the encoder has tabs on it. I think I got one right here. So probably better for you to see anyway. And these are referred to as variable reluctance or reluctance encoders. Guys, it's taking a little while for my computer to update this. Huh? She got it at well, all that I don't see it. But a variable reluctance basically would come up, and must be on my computer at home. So what we have a circle, and then we have metal tabs sticking off of it, which would be kind of centered to the controller. And what we do is we have a magnet pickup. Sometimes they're just